So I see only have a couple of you here, but so this is the second last class, and then I guess we probably have a little bit time to talk about like reinforcement learning for the last class, and maybe we can talk a little bit about reinforcement learning even today. I probably won't spend the whole lecture talking about this doing Turing machine. Um, this is something that uh, in terms of deep learning, I guess it's a little bit old stuff, like it's back in 2014, but it's quite interesting stuff. So therefore, I like to mention this here. So this new Turing machine, I guess I assume that many of you know like was Turing machine. Like by the way, like how many of you guys are here? Like yeah, okay.
I think like just two.
Okay, I have two. Yeah, only two of you are here actually, honestly. So, but hopefully, okay. So, yeah, I guess I don't need to explain. I don't know. Do I need to explain like anything about Turing machine? But I assume you saw that like in some computation. I mean computer science class there, like computational theory. So what we'd like to talk about today is like this so-called neural Turing machine. As you can expect, is a neural network version of like Turing machine. And to start with, like this is a memory model. So again, we just went and talk about like, for example, like this attention model, like bird and so on. I'm just saying that like RNN is not getting as much flavor recently for the last couple of years because the rise of those attention model. Um, but after all, I guess a memory model like RN is going to stay because you think of like a real problem that we need to solve is always like we need some kind of memory. Like for animal, for human, like we have some actual task, we always need memory to solve that. Of course, we in the sense like even though like we looked at like for example attention model like bird model, it's not like they don't have memory, just it's hard print into the model. Basically, we train the model completely, and that memory is basically is the model. It's like it's hardwired into that model. So, but of course, like for RNN and also like for maybe LSTM and so on, this is like um, involve like more short-term memory, or like you can think of like short-term to medium-term memory. So, but for algorithm, like say for example, if you think of any other algorithms like we do computing, it always involve like using some RAM and like some kind of temporary memory. So, and in this case, like that's whatever like what what we talk about today. Like this, what neural Turing machine is supposed to do. So it's kind of like imitate like a Turing machine, and it want to make it um, unlike RNN, it try to tackle problem with more classical computing. Um, for example, like you have like some sorting problem, have some whatever problem you can think of. But imagine that like I don't want to write a program. Can I train a kind of neural network models to kind of like do this task for us? So of course we need memory. We need external memory for that, and you can't expect that we need like quite a lot of memory also like larger memory. Um, if and my side also like this memory the capacity need to increase as like the the capacity of the task increase, and so like to show photo of these two guys here. Like I guess maybe you recognize the left hand side, the guy on the left hand side. I don't know like whether any of you recognize him. Um, uh, he's homosexual. Actually, from the look, you can kind of uh, uh, I'm gonna see a little bit. But anyway, like his Turing, like I'm not sure you watch the movie like Imitation Game, he
Yes, yes, I've seen it.
yes
Uh,
yes he was in the
Brilliant mind.
yes, and uh, he probably was like someone suspect that he is. They said that like, either he was suicided, or like he suicided, or like he was kind of like killed by the British agent at that time, because like he was openly um declare himself to be gay, like at that time. Of course like that, of course I am his public figure, and maybe the British, I don't know, doesn't like that, didn't like that. And he was a World War hero also, like because he was involved in those like cracking the Enigma, the German what's that called, encryption system. And the guy on the right, I'm not sure you know that he may be um I don't remember there's any movie about him, honestly. Uh, but he's definitely a genius of the last century. He's from Neumann. Uh, how to spell Neumann? Okay. Anyway, it's from Neumann, and and he I read some stories about him. He's actually not only he was a genius, he's also like a party animal. It was rare at that time, like also like being alert. And he always like have like party in his home, and he also like to kind of buy a new car every year or something like that. Um, and of course, he had contributions in almost every areas in science. I mean, like in natural science, physics, math, like economies, and so on. Like if you know the Lash Lash equilibrium and so on, the in game theory, like he has probably like as much or even more contribution on game theory than even Lash. So and also like the modern computing architecture, like many also like give credit to von Neumann as well. Um, and Turing machine, like as I mentioned, like maybe just a reminder, like what is it like? It's a very much theoretical model. It's just say we have a paper tape here, and we have a head to read this paper tape, and you have this kind of like controller. You read one kind of like, I don't know, character at a time, and then like you decide, control the controller, whether you want to move forward and backward, and then you can read and write and so on, and erase and whatever. And you can show that like any computing model, like except maybe except quantum computing, the computers that we have right now all can be modeled like using a Turing machine. And Turing machine like is very powerful, and actually like when you have a computing device can model a Turing machine, like you will say like this is the model is like to be Turing complete. And actually one can show that like our NN is like actually Turing complete. And as I mentioned, like here the end goal is not trying to kind of construct another model to replace our computers, but instead like we want to build a model to be automatically generate program. So it's like we want to replace the programmers really. So so it's like basically learn from data. Like you give a bunch of data like to a program, and hopefully it will generate a program for you basically. But yeah, to the network, I'm trying to generate a program, something like that. So yeah, I mean, can we do that? I'm sure we can do that. And this is just an example. It's trying to learn a memory copy. Like if we have, okay, I will show later on also the actual task there. It's like you have a block of bytes here, like have like so basically you just have basically copy this part to like to the output, something like that. Like we read this part here, and then you copy it back, like something like that. Very simple task, but you see like how this can be done like using a neuron Turing machine. And so how can we train the computer to write a program? And so first of all, like you think of like what we have up to now is always like the same paradigm. We kind of have a network model, and we have some parameters we can train, and then we have objective function. Then we use backpropagation uh, to kind of like find the gradient of those parameters, and then I use optimizer just to tune those parameters. So it's basically the same thing. So but the problem here is like if you think of like a regular computer program, let's say if I need to access some memory somewhere, so this addressing mechanism is generally discrete, right? So because it's a discrete step, uh, it's impossible, or basically it's not differentiable, right? So therefore we cannot use backprop. So the main trick here is that we try to do some kind of soft addressing. So we want to be able to address a memory block, and this addressing is like kind of like not hard. It will be like soft, and so it will be differentiable. So therefore we can still use backprop. And essentially this soft addressing is actually just attention, like what we have like earlier when we talk about BERT and other attention model. So so first look at like what the actual detail of the model. Like we have the memory block will be just a matrix, like let's say n by n matrix here. So it'll be like this. So each row you can think of this as a memory element. So unlike like you have a RAM typical computing structure there, that you have a byte as a unit, we have like basically a vector as a unit here. So now in terms of addressing, like we are not going to read one vector at a time, but we will read all the vectors at the same time, but it will be kind of weighted sum. So this will be like W will be like a addressing vector for that. So you think of this as the entire memory block. So we'll read our vector as weighted sum of this W with this memory block here. So and we have this weights here will be normalized, so sum over to 1. So this is the main idea. That's actually the key idea. So and afterward will be just how we kind of modify a little bit so that like we create the entire model. But this is the key idea here. So because this mechanism, like you see, this addressing mechanism is just weighted sum, right? So this will be therefore will be differentiable. So everything is differentiable. You can just generate network, and you can apply backprop, and then you can do steepest descent, atom, RM's pop, whatever. So this is like reading from the memory. So now to write into the memory, we will at least for the initial model for the new Turing machine, will be like that. We have again like we have an access vector here is W. So and we have a erase vector here, E here. So basically, by the way, this T here is the time step. So this is a time step T. So and I have a E vector T, ET here, and I have W here. So in this case, you can see this is a just a element-wise product. So what you see is like if I have W, for example, like I have W, maybe my memory block is like maybe just 3 vectors here. I have like originally what do I call that again? M1, let's say M1, M2, M3, and so on. So if I have my WT here or W here, will be like 3 values here, and maybe like 0.1, maybe 0.9, and 0. So this is saying that I basically I'm going to replace this part. So I'm going to replace this part. So I will erase this part first, right? So therefore, like I will kind of have a okay. I have this ET here will control like okay, this ET here, let's say if my ET is just all 1 here, and maybe instead of like 0.1, 0.9, 0, maybe I have 0, 1, and 0. Then for the middle vector here, basically we'll just remove it. you see that like I have like this will give me one, this is just a unit vector here. Unit vector minus 1 times this all one vector here will just get me also vector. So this multiplied by this also vector, I will just make it 0 here. So but I can make it less extreme. So I can have these two possible control parameters here. I can have this w instead of 1, I can have like say 0.9. Then I will get basically only tune it down to, instead of like this is all 0, now I guess 0.1 like for the entire vector here, 0.1, 0.1, and so on. And I have additional flexibilities from this ET here. My ET here can also be not maybe entire vector is 1. I can like maybe just erase part of this in the vectors here. Maybe I have 1 here, and then like the rest is 0. Then in that case, I will be just erasing the first element of this vector M2 here. So this is like it did the erasure here, and then afterward like it will just add this back. So when they add it back, like it will be just like W multiplied by this A here and add back to the memory here. And again, like this A will be some additional flexibility for you to adjust like what you're going to add. And this AT, ET, and so on is like it's trainable basically. It will it can be it will kind of like be different like at different time step, and this will be like spit out from a controller, and you're trying to train that controller basically. This is like again more precisely the whole thing here. So let's see. So okay, first of all, like we need to design the W, right? This one is like basically like given the previous state like W, and the current memory block here is trying to spit out the next W like in the future, and also like depends on like okay you have the current state here, and also depends on your current input. You basically have a controller and will kind of spit out some of these controller outputs here, and this will be like control each of these steps here. So let me go into like each of these steps here. So for the first step, like we will kind of construct this W here. So W here, this is a temporary W here. So this WC will be just basically will be like a attention model here. We will have a key somehow. This key will check with the entire memory to see like which one is best matched with the key. Basically, in the memory block here, the key will look into each of the memory block like M1 and so on, and just match with them. So the matching will be just done using an inner product. So I'm also like addressed by this beta t here is some key string parameter. So again, like for both of these keys and also this beta, it can be it's actually spit out by this from this controller. And okay, by the way, the controller here later on you see is just a you can be like LSTM or RMM, RNN controller. So based on like your input and the current state, it will try to spit out these things here. And then I have this WTC. Afterward, like I would just say it has an interpolation step. This one is actually just it's really, I would say, it's like an inertia. So it is similar to like what we have in optimization, like we put this momentum things like in optimization basically. So instead of like just use the current WCT, we'll just say also put a part of the previous WT minus 1 into the current WT. So then afterward, we'll have this spreading. So we have this WT generated, I would call this spreading. It's like in the original paper, it's called a circular convolution. But you see, like it's basically just do a low pass filter of your current WTG here. For example, typically you have this ST here, the filter applied to that is something like this. So you just kind of, instead of like you have a pretty sharp adjacent vector here, after this kind of like low pass filter, just like smooth it out kind of. And then afterward, like it sharpen it again. It's a little bit weird, but know that like for all these like parameters for kind of for spreading and also sharpening can be trained also because it's like spitting out from a LSTM algorithm. So then finally you have this WT. So this you see like how this WT like uh, was updated like for each the steps. So you have this know each of this WT and also like earlier like we supposed to get trained with this ET and AT. So now then like basically we have all the elements. We just have a model that you have this WT is update each time with this controller outputs that the controller is basically LSTM or RNN that is based on the current input and the previous state. And also the controller will also spit out the what we just mentioned like in the addressing, in the writing that we have this AT, ET, and RT to read the. Do we have RT? I forgot. We don't have RT. Sorry. We have this ET and AT to write the memory. So that's actually the entire model. So then you can train it, right? You can train this and try to solve lots of problem there. And in the paper, actually, they mentions several of these experiments here. So let's look at each one of them. So say we have this first one is a memory block copy. It's like what we talked about like earlier. So we have basically, let's see if I have a better slide here. So we have some of this memory block like this is a target, and then it's trying to copy this like to the same thing here. So as you can see, like this is a let's see, this is 10, 20. I think this is length 20. So during training, only train up to a block of length 20. So therefore, like it also try to see like whether the model can generalize. So therefore, it try to see like how does it work like when we have a longer length like 30, 50, and 100, 120. You see it works kind of okay. Like it has made some mistake like when you get longer, but presumably like it's kind of work. So but that is actually for the neural Turing machine. You can try to do the same thing use LSTM alone, and that just doesn't work well at all. So it works. It's good like when you just like as you train like up to 20, you also like test up to 20, you just work well. But if you try to go beyond that, like it's just starting to have problem. This is all this problem like when you try to generalize. And one thing is kind of interesting is look at like what the WT is like as time goes. So this is a WT vectors, this is a time axis here, and this is a WT vector like for basically the adjacent vector like over time. So you see like when we train the model, from this WT vector we can see like it's very clearly what the model is actually doing is precisely trying to copy the input like to each of this location, right? So it start with like okay, copy like from here at this time step I copy to this location here, and then to this the next location, the next location. So each time you read one vector input here, then you copy to the next location here. So when it's reach the end, then like you just stop, and then like you you stop, and then afterward, like you start reading from the memory. Now when you read from the memory, you're also starting from the the one that was, maybe I should use a word, was it, from this one and go upward. It just make total sense basically. um, and this is just memory copy with like one block. Now let's look at like repeated memory copy. Basically we try to memory just copy a block several times. So what they try to do during training is like it will try to copy like 1 to 10 times, I think, like, and also the block size is like 1 to 10. So and you can see like because it's trained like with a block size like up 1 to 10, and also like, it's like repeated like with only 10 times during training. So this is already doing generalization because the length is like 10 now, like each block is 10, and repeat 20 times. And for NTM it's like generalized good, like, so like when it try to repeat like 20 times it work well, and also like when you extend to length 20, the block of length 20, and repeat like 10 times, it works pretty well also, even though there's a mistake here. And for LSTM again it doesn't work, like really when you generalize it just doesn't work. So let's see, but let's see, cause post sequence. I don't know. I'm thinking whether this say anything. Okay. Also, like training is faster even. So you see, like um, for NTM, it's actually training faster. For LSTM, it's not just it's generalized better, it's actually trained better as well. Uh, and also like again, it's interesting to look at the W vector again. So in this case, like you have the input, like you try to adjust again, like you're going to like write at each of these location when we try to copy. So for each of vector you read in, you write it into like each of these location here, and once you're finished, then it will read back like from this location consequently, and for repeated number of times. And this is a memory copy. And there's another task they look into is this so-called associative recall. So what they did here is basically you have a number of block here. So you have start with a symbol like this. So then you have a number of like 6-bit blocks here. Like you have different number of blocks here, like first block, second block, third block, another block, and so on. Now, after you read in all the blocks, then we have another special character like to here to indicate, okay, we start trying to inquire like, so what trying to inquire is like you're going to like repeat the block appear before, and trying to kind of like read out the block like after the block that we just like inputted. So therefore like, it's supposed to output this block here. So it's the task here. So therefore you can see like afterward just this block here. Right? So now like you see like the again like how W the vector goes like as we increase time. Again like each times it just like write into one memory block at a time. You keep writing on that, and then doing output. Then we just say because we are supposed to read out this one, so we're trying to read out this one. So again, it's pretty reasonable. Actually, for this task, let's see. Yes, during training, like we have at most 6 items here. So therefore, like when we have more than 6 items, then again, like this is trying to generalize. So during training, we only have like the total number of blocks here, this is only, for example, here is only 6 blocks here, so we only train up to 6 blocks here. So then during testing, we want to see like if we have more blocks, that does the algorithm still work? So, and you can see like LSTM fail pretty quickly, like and for NTM or also actually NTM using like you can use LSTM controller. Also, they try like using fit for a controller, and both of them work much better than LSTM. And another experiment they try is they try this n-gram model. Basically, like the n-gram model is like just an you have a sequence of bits coming in like 0, 1, 0, 1, 0, 1, 0, let's say. And the bits are correlated. For example, I have a 6 gram here. It will be like correlated in the sense that each 6 of them is kind of correlated somehow. So therefore, like for this bit, the probability of this bit will be kind of like will be conditioned. Will depends on like the previous 5 bits here. It's like a Markov model, but it's like Markov depend on the last 5 bits instead of just the simplest Markov just depend on the previous bit here. So and then like so for example, like based on this, for example, if I see this here, the probability of seeing keeping a 0 or will be like, let's say 0.1, and having a 1 is 0.9, let's say. And they have this like basically they have this generate a model like this, and then they just run it like simulation and try to have the NTM to estimate to recover basically the estimate here. So of course it's a probabilistic model, so therefore you shouldn't get like what I mean like perfect reconstruction compared with your input there. So but if you use a Bayesian optimal estimator, you will have a cost like this. And here they again I also compare with LSTM and so on. And also they did better than like LSTM. And so this is like the actual input and estimate here. So basically you have an input here is trying to estimate what each of the bits what is supposed to be, right? So this is the optimal estimate here. The color here is I mean the intensity here is indicating whether it should be a 0 or 1. So if it's more it's whiter, it's brighter, then it will be more 1. If it's darker, then it will be more likely to be a 0. And so and also it's kind of interesting to see again this weight vectors as it goes with time. So what is indicating like in this one here it's like you have an input like this, and the green arrow that's pointing here is let's see. Yeah, it's whenever it's a pattern of 0010. So you can see that like whenever I have 00010 here, that means like black, white, black here, then I have a green arrow here, right? So and here also like a here is a black, white, black. Here I have a green arrow here and green arrows here. So what you can see is like whenever it have something happen, then it will try to white at this location, right? And it also look at this another context, like another combination. That's like 0, 1, 1, 1 here. So whenever I have 0, this is like black, white, white here. I'm going to white at this location. So this location is, maybe I use the color of arrows like this location is I'm writing to like 0 when since the context is 0, 1, 1, 1, 1, and I have like I see this one. Basically, say when I see a context 0, 0, 1, 0, I will write at this location here. So and what the author is suspecting is like, you see, like it's writing like at the same. It makes sense, right? You're writing at the same location whenever it's writing, but at the same time, like, they kind of reduce the intensity. So it looks like it's doing some kind of counting. So I mean, each time you are when you see this context here, you are writing a current value to there, but each time you just reduce the intensity a little bit. So this is similar to um, I don't have a slide for that, but this is a um, this is like basically, if you think of that, like why is so, because this is like um, kind of like some kind of like of moving average, right? So I want, when I estimate, because I need to estimate whether this should be 1 or 0. When I'm getting more and more counts for this context, then the weight compared to what I already learned should be getting smaller and smaller, right? So and this is basically totally captured by the model here. Uh, so, but anyway, I guess I won't go further for this one here. So and also, like, I think this is probably last. They also try a task like a parity sort model. Basically, like, you have input here, but you also like impose the parity of this input here. So you have, this is the input. I'm saying like what should be the parity. So this is like the higher, yeah, the 1, 2, 3, 4, 5, 6, 7, yeah, something like that. You see, like, the higher the value is higher priority. So you can see, like, over the entire one here, this is the highest priority, and then the second highest, and the third highest, and so on and so forth. And then, like, you should sort it out. The target should be like, so because this is the highest priority, so this go to the first one, and then this is the next highest priority, so it goes to the second one, this one, second one here, and so on and so forth. And so it looks like, okay, again, this is the weight diagram. I mean, this is, no, I should also say this is the weight vector as it goes along with time. And you can see that, like, what they are doing is very similar to oh, by the way, like, this I should mention this priority is like from, I guess it's not indicated here. If I remember correctly, it's probably like from 0 to 1. So what they did is like, they based on like this value of this priority, they kind of like adjust to the location that is proportional to the priority. So for example, like, if I higher priority, I'll adjust to more to here, and lower priority, I'll adjust to here. So for example, if I start with, actually probably that one is flip. This probably is higher priority. This is lower priority. So then, like, when I read in the input, like, I have a certain priority, maybe priority 0.3. So it will be approximately, this will be kind of waiting at this location. This is a maybe 0.3 here. So in terms of like 0.3, okay, if I say this is 1, this is 0, is approximately 0.3 here. So, and then maybe the next, when I, for the next vector, maybe a priority is 0.31, then I will just write to here, and so on. So once you write everything into the memory block here, so when you try to have the priority sort, you just read it out according, like, from the highest priority to the going up. of course, there will be some location that you didn't have anything, so you will skip that and so on. And this here, I'm not sure. Like this looks like it's kind of some kind of like um, problem with the model. Supposing it would be all kind of monotonic, if but it's pretty close to be monotonic anyway. And this is the cost for the priority sort, comparing with like LSTM and using two different controller. And so and this is a little bit detailed, like for the actual experiment parameters. This anyway, like it was a little bit dated now. This is 2014, so therefore they use RMS pop at that time, and they use momentum upon 9. And I don't think I will go into details for these parameters here, but it's just like showing like what is the um, memory size and the controller size and so on. The controller will be like based on whether you're using LSTM and so on. Then will be like I think like this may be like a feed-forward latch where the controller size probably is like the number of hidden units and so on. And yeah. So they have a follow work actually in Nature, like in 2016. They call them like differentiable neural computer. And actually there's a blog post as well, like in DeepMind website. And the idea is just an extension. So because in the neural Turing computer, neural Turing machine model, it only have like one addressing mechanism. Basically, it's like an attention mechanism. But you can imagine that in many actual problems, like we will need to have some kind of temporal, kind of like, for example, like you may write into certain order, then you may need to read out in also the same order as well. So we want to have some temporal mechanism here, and also like we want to make sure to, I mean like for the original model, it doesn't have any mechanism to see like whether you are writing like the memory that is already used and so on. So therefore, like in this updated model, they have this a usage monitoring mechanism that allows you to keep track of like the usage of like those memories. So then like you can see like for these first two, like it will also determine, can modify how your read mechanism, and the first and the third one will control like how you write. And with that, this is actually a nice kind of like, maybe I just play this here. It's a nice, I don't think it has any sound for that, but this is just a nice illustration of like a possible example. Like it's like using the differential neural computer there. So it's just like look at like say like a pair of relatives, like who is who and something like that, and then afterward it's trying to find the relationship of a pair. So for example, after they're building the entire graph, they ask like whose failures, like maternal grand uncle, then she's able to find that, something like. So this is like an illustration of like of the use there. So this is just a quick conclusion slide that it's kind of a very interesting, I guess, like work and direction that I didn't have like too much update myself like to check on like what's the latest work there. So, but yeah, I think like it's interesting enough. Like it's definitely worth like spending some time like talking about that. So we have this NTM is actually think of that like it is a memory model, and the main innovation I would say is like the addressing mechanism. But this is not exactly new. It's just combined into this kind of model. So because you have this kind of addressing, then you can have a differentiable model. Then they have the entire thing is a little bit hard, I would say. But then you will just like train a controller to kind of spit out these parameters to have this width wide um, um, to yeah I mean to change the memory, basically to access the memory, to change the content of the memory, and also to spit out the output. um, and they have like quite a lot of experiments. It looks promising. Of course, all these are kind of toy experiments. And then they have this DNC just try to improve this NTM just to have better, yeah, kind of like you can think of a better memory management, because um, for the original one you don't really know where like the memory is used or where it's unused. And also like they add like additional feature to allow you to kind of keep track of the tempo, like when did you write something like that. So this is like pretty quick. I guess I spent okay three uh, 2/3 of the class on this, I guess. So what any questions like? So if no questions, let me if I don't. So the next thing I'm going to do is probably talk about the last topic like of this entire class. So let me just use a oh, let me just use a whiteboard. So okay, I'll just sketch first. I guess I maybe talk a little bit about reinforcement learning, like on a whiteboard. Then next time maybe we'll go into slides. And so I like to spend a little bit time on reinforcement learning. So like so, but the idea like I mean, of course I will later on I talk about deep reinforcement learning. So it will be deep like in the sense is I just mean like adding a neural network or something to that. So for reinforcement learning like uh, of course like we spend quite a lot of time like I don't think we spend much time on like uh, uh, unsupervised learning. So and most of the models we talk about actually is kind of supervised. And also like of course like the problem of having like a supervised model is like we need to have labels, like we need to have everything, like we know the quant truth, we know what we're expecting completely. And if you think of like unsupervised learning is one extreme, that you don't have any label, you give the data, you just want to extract whatever information like given the data, but you don't know anything about the ground truth. So reinforcement learning is kind of in the middle. So you know a little bit. Compared with the actual label, it's like very little bit. For example, like a very classic example of reinforcement learning would be like autonomous driving, for example. Like so maybe I have like I can see this okay, I'm drawing like very weird. So maybe this is a steering wheel here, and I can see outside, right? This is my input, and I'm trying to create an agent to control the steering wheel, just move the steering wheel. Maybe like I have a brake somehow, I have a accelerator, I have a gas pedal here. Um, and Now, I mean, if it's a supervised learning, it will tell you exactly when you see these scenarios, right? When you see uh, in front what you see, you're supposed to steer the steering wheel for maybe like 15 degree, and then like you surpass the gas pedal like for how much, right? That would be like supervised learning, like give you the exact instruction like what you're supposed to do. And for unsupervised learning, I don't know what to do, what we can do. Like it just doesn't give you any information. You just give you like what you see here. I don't think you're able to learn anything. So you just see like, okay, if the car is moving, it's moving like this. Okay, try to figure out what I don't know. Now the more realistic model will be like this. Reinforcement learning will be I I I see something, and then I have this agent trying to steer the, I mean control this car here, and I will have basically just have some guy like also in the inside the car to teach this model, just saying, okay, you're doing good, you're doing bad, okay, don't do that, or something like that. You give a very simple instruction, just saying, you're good, you're bad, like this is not good, or something like that. Maybe even like in the more extreme case, maybe I don't even have something like that. I'll just let you drive and may crash. Like you get the feedback saying, okay, you just crashed, so you're doing really bad, or like you're driving like you want to go to Walmart, and then you went there, you get um, extra, I don't know, points like for successfully getting into your destination. So that's the basically what reinforcement learning is about. Now I and of course like for reinforcement learning here, like we don't know, basically we don't know. uh, you can okay, also I should actually maybe I should you can think of like uh, we have this agent here we are trying to train is some kind of like uh, very brainly agent. I'm trying to draw this is like a brain here, and I don't know, and maybe from the environment, like from the world here, I'm trying to observe like uh, the current state. The state can be like what I'm going to observe, like what can be like in the autonomous driving will be like what I see at this moment, and then like you have an instructor maybe next to you to say that whether you're good or bad, like doing at this moment, then it can give you some kind of reward also. And based on this reward, you are trying to do some kind of action, right? So the action will control, will affect this world here, and then you will get like reward states according to your action, basically. So to model that, like uh, a very classic model is known as this. Actually, it's not even, it's probably even before like people talk much about machine learning. This is probably in control. It's like this Markov decision process. How to spell decision? Okay. Okay, Markov decision process. So the Markov decision process is like um, it is a model basically described like this. So we have just like what we have here. So we have state, the current state. State is S here. What's the current state that we are in? And we have reward. So what's the current reward? Let's say. And I have action also, the action of this agent, the intelligent agent, the action A here. So based on my current state, and my current action, then I may transit into another state. Let's say I transit to another state S pi here, and the transition probability will be described by this T matrix here. Maybe it's not a matrix, a T function here. So for the current state and whatever action you give, I have this S pi here. You can think of this as like some kind of probability, or maybe I just write it as P here. Oh, so then okay, maybe it's not good. I should write P here. So I can write P. So you can think of like this is like the probability in the next state S pi. Will be this conditional probability S and A should be like something like described by this T function here, this transition function here. And also like based on your current state and the current action, your reward in the next day, or your new reward will be something like some R function that given your current state, your current action, maybe also depends also on the future state that you will fall into, that will be your reward. And to describe the entire, to complete the description of the entire model, you also need to know the start state here. You know to the start state somehow. What's your start state? Where's like some kind of S naught here? Where is the original state? And maybe you want to have a terminating state also. Maybe I call it Sn, let's say. I don't know. So maybe your objective is go to Walmart, and then maybe like when you reach like Walmart, it will be like the end state, so you're done, and then you just stop the model here. So and this kind of like the Markov decision process. So this, you can think of this as a P reinforcement learning. At least it's a large fraction of reinforcement learning can be understood like with Markov decision process here. But the main difference of Markov decision process from like reinforcement learning is that we in reinforcement learning we don't know this like T and R here. Like we don't know what's the basically the transition function. I don't know what's the probability here, like what I do is supposed to be like that, and I don't know what will be the reward here. This is something I'm supposed to learn. So is that clear? So now let's see. I regret that I write everything here. Now the space is very hard to use. Maybe I erase somewhere here. Okay, so let's see. I have 10 minutes. I guess I probably have enough time for this. So now I have a Markov decision process. I model like this. I have T, I have R. I know this kind of stuff. So then the question is like, what should be my strategy? So, or actually more typical people call it like policy. So the policy will be something like, for an agent, like this is a policy of an agent, will be something like whenever you have a state S, so what are you going to do? So like it is kind of like a mapping. So from state S, like what you're supposed to do. Sometimes like this policy will be many times people will choose a kind of it can be like deterministic, or like you can be like probabilistic. Maybe I just assume like deterministic. I would say like policy this mapping like pi here, like to denote this, I have a policy pi here. So that basically map into some action. This is my actual action. So whenever I have state s, my action here will be like pi s. I will do pi s. Now then the problem of my market decision process will be, given this decision process model, like how do we find the best policy? What is the best policy? So the best policy, of course, is like all the problems we're considering in this class is like, again, we're trying to maximize some objective function here. I mean, in this case, the objective function will be the reward. But of course, like, the reward will keep changes, right? So we want to maximize like actually the accumulated reward. So we want to maximize the total reward. And but typically, like if you just maximize the total reward, it may not be fair. Just like in economy, you like to add a discount factor somehow. This is some kind of discount factor. So for example, like would you rather I gave you like the kind of like $100 today, give you $100 today, or like give you like $120 like next year, like something like that. So of course, if I say like I give you $100 today, alternatively I can give you $101 to you like next year. I guess like under the current situation, most people will suggest will agree that I better get this $100 today. So what I mean is like you same thing for this reward, like because you see there's a time element in this problem here. So your state actually keep changing one time at a time, at one step. I mean, state like one interval at a time, and we really want to get the reward. Most of the time, we would like to get the reward sooner or later. So therefore, actually, the actual objective, like maybe I put it the loss, like this is not the loss anymore. Maybe I should get a better notation for that, a better symbol. Let's say the mm, mm, mm. I don't know. Anyway, I cannot think of very good. Maybe I just use W for the moment for the total reward. So what I mean is that instead of like summing like R, maybe this R that we have as a as pi here, we're summing over actually different time step like T here. What we're interested in, so instead of like maximize that, what we are interested in typically is like maximizing like with some gamma times this RT as pi here, and this gamma will be to the power t, something like that. So t can be like, for example, like t is equal to 0, that will be the current time, t equal to 1 in the future next time step, and so on and so forth. So we have a kind of like reduction here. So and we want to just basically maximize this discounted like total reward here. And so okay, then next thing, maybe I'll just give two more terminologies here, then like we'll just end somehow. So so let's say I have the value of the state. I would say a value of the state that actually typically have a V star. Value of a state will be something like, oh, by the way, this, okay, actually it's good to use U here, because this is also like known as the utility actually. Yeah. So this is the utility here. Oh, and by the way, like one thing I also like this here. Of course, I can't write this in a kind of a little bit sloppy way. This S of course changes as time with time, right? So I put ST, AT, and S by T here, and also like because we have this transition like from state S to S pi here is like kind of stochastic, right? So it's not every time it's the same. So therefore, like even though you have like an action here is completely deterministic. Basically, if even your policy is completely deterministic, your rewards return out won't be deterministic, right? Or like the utility, the total reward or the total discounted reward won't be deterministic. So therefore, like what we when I say maximize, is actually maximizing the expectation of this utility here. And now V star here, we call this value of a state is basically if we do the right thing, basically if we have the best policy, let's say this is an aperture policy. Let's say if I have best policies, it's called a pi star here. So this is the best policy. So the best policy will be like the policy that maximize our utility, our expected utility here. So if I have this best policy, pi star here, what will be my expected utility if my starting state is S? So this is saying that, okay, if my starting state is S and I do everything is right, what will be my expected utility? And this is basically defined as like this this utility here, given my policy is equal to say pi star here, and my initial state here is equal to S. So this is like we say like what's the value of a state. Now we can define one more terms here, and this is like the Q star. Q star is like basically how should I say that? Maybe before I say Q star, let's say like here I'm saying S is just a state, right? But I can also define something called Q state. A Q state would be something like that. We have the current state S, and if we take an action A, that will get me to some new state, right, potentially. But I don't know what state I will go to yet, right? Because this transition is deterministic, right? I don't know what state I will go to yet. So I'm in a meta state, in the intermediate state, though that I may go to some S pi 1 here, or maybe go to some S pi 2 here. I mean, I don't know where I will go to, but I will go to some of this state. And I will call this meta state, I call it like Q state. And a Q star will be basically the utility, the expected utility, or expected optimum utility under this Q state. So more precisely, this Q star SA will be just equal to, again, this expected utility when your current state is S, and then your action is A, maybe I don't know, this is see the A equal to A, and your policy is the best policy, pi star here. So I guess I will stop here. Do you guys have any question? Like this is actually, I think like if I use the whiteboard, I think I actually explain more clearly. Do you guys find that way, or like but I will repeat some of the stuff like next time. But I think I covered quite a lot about like the Markov decision process, and the next time with this definition here, we can easily find what is the optimum policy, the best policy. And then next step will be just, okay, if we know how to solve the Markov decision process, then we have a new problem. Will be something like trying to learn this TMR. This would be one way to do that. Like once we have a new reinforcement learning problem, we can try to learn the environment first. We learn TMR, then when we know TMR, then we can solve that like a Markov decision process, right? But alternatively, typically people will doing this at the same time. We're trying to solve the problem itself, like that, and at the same time we don't know exactly this TMR, typically using the so-called Q-learning, and there's other approaches as well. But yeah, we will talk more about that next time. So if you so do you guys have any question, comments? If not, then I will just stop like here. And by the way, like remember like your final project, like I put up this kind of assignment for the final project in the in Canvas, so you guys can go can submit it there. Again, the due date will be actually due date is pretty soon. Like will be actually will be 2 weeks after our last lecture. I mean my class in Thursday. So and okay, and then I